Well, so thank you to be here, and I want to thank Sergey and Gary to give me the opportunity to talk about black holes in low quantum gravity. And somehow I will a bit complete what Carlo did this morning, trying to explain you how we construct and how we define the microset of a quantum black holes in the case of loop quantum gravity. So before going to the black holes, I wanted to start to recall the history of loop quantum gravity. And loop quantum gravity starts with an history of connections. Connections because the way we quantize gravity within the framework of loop quantum gravity is that we start with HTK variables. So HTK variables, maybe I need something. Where is the laser? The pointer? Oh, okay. It's coming, yeah. So I wanted just to start that the quantization of gravity within the framework of low quantum gravity is based on the HTK formulation of gravity. And in this formulation, the fundamental fields are a connection and the conjugate momentum, which is an electric field. So in this theory, gravity is very similar to gauge theories. So the idea was at that time to mimic the quantization of gauge theories like Yang-Mills, SU2, to say something about quantum gravity. So at the beginning, when HTK discovered his formulation, the theory was complex. So this is an important point to remind for the rest of the talk. And in this complex formulation, as I said, gravity is very similar to Yang-Mills theories. And the problem is that as the theory is complex, we don't know how to start the quantization. In fact, the theory is a kind of gauge series with a complex gauge group, and this is something that we don't know how to handle and how to construct the physical hyperspace, the space of quantum states. So at that time, it was not possible to start the quantization, and there were no hyperspace for quantum gravity, nor at what we call the kinematical level, nor at the physical level. I will go back to these notions later. And then, almost 10 years after, something happened in low quantum gravity, is that in fact, this formulation of HTK, which was complex, we realized that it could be reformulated in terms of a real gauge series, where the gauge group now is a real gauge group, which is SU2. And this is something very, very important, as we are going to see. And in this formulation, there is a new parameter that enters into the theory, which is classically totally irrelevant, but at the quantum level it will play an important role. I will come back to this later. But even if in this formulation some of the constraints get more complicated than what we have here, at least we can start the quantization of the theory of quantum gravity. And then we leave aside some problems that we hope to solve a bit later. So now we are at this stage. We have a theory of gravity where the variables are a connection and an electric field, so the coordinate and the momentum. And these are conjugate variables with a free parameter gamma here, which is called the Barbero-Mirzi parameter. As we are going to see, this parameter is really important. And this parameter, as I said previously, it was written in the previous transparency, it labels a family of canonical transformations. This means that, in fact, gamma has no physical relevance. And it is possible to view that gamma is totally irrelevant at the classical level from an action principle formulation of HTK-Barbero formulation of gravity, which is this one. And we can show that if we start with this action, we end up with the HTK-Barbero formulation of the Hamiltonian HTK-Barbero formulation of gravity. And this parameter here is a totally free parameter that disappears when we solve the equation of motion on shell. In fact, in this equation, we can show that omega, which is the spin connection, is a torsion-free connection with respect to the triad here, which contain the information of the metric. So now, yeah, we have gamma which disappears. So this is the classical setup. But at the quantum level, if we start the quantization, this is possible. Now we have, as I said, because we have an SU2 gauge group, and we can use the techniques from gauge theories to quantize theory. And then we see that this parameter gamma will play a very important role. Why? Because it enters into physical prediction somehow. One of the main results of loop quantum gravity is that area and volume and all geometric quantities become operators, exactly as the energy is an operator in the case of quantum mechanics. And these operators, they have a discrete spectrum in the frame of loop quantum gravity. And that's really important. And you see that, for instance, in the case of the area, there is an area gap. So we have nothing, and then the first excited state, quantum state, comes with an area which is given by this quantity here. And gamma enters in this area gap. And this formula will have an important consequences when we study quantum black holes and thermodynamics of quantum black holes in the case of quantum gravity. So you see, there seems to be a conflict between the classical aspect and the quantum aspect, but we are going to come on this aspect in this talk. And also in cosmology, we cannot see here, we can show that gamma enters also in the maximal density energy of the universe. So, as I've just said, there seems to be a puzzle between the classical aspect and the quantum aspect of loop gravity. And then what I would like to address in this talk, to show in this talk, that it is possible to solve this tension. And when we solve this tension, we have a new insight and new ideas about how quantum black holes are described in the context of loop quantum gravity. So this puzzle is a main recurrent question concerning loop quantum gravity. So why we have a classical parameter that has so important physical aspects at the quantum level. And also, this question is very important because it's related to another property of loop quantum gravity, and this property is the discreteness of the quantum geometry. As I said, one of the main predictions of loop quantum gravity is that space is discrete, in some sense. And in fact, this discreteness is really due to the fact that we work with the SU2 gauge group, which is a compact gauge group, instead of with the initial SL2C, which is a non-compact Lorentz group. And gamma is the parameter which transforms somehow this SL2C into an SU2 compact group. So understanding gamma is also related to understanding better the notion of discreteness in loop quantum gravity. So there were many proposals in the literature to solve this problem, and here I will show you that it is possible to have a very natural solution of this puzzle, and this is related to the fact that gamma, this parameter, in fact, should be complex. And it should be complex for some reason I'm going to explain you. Okay, so this was the motivation of the talk, and now the overview. So before going to the black holes, I will start in the first section by talking about loop quantum gravity, so just giving the main ideas of the theory, where I will recall the foundations of the theory at the classical level, and I will say how do we proceed for the quantization and how do we get the discreteness of the space. Once I recalled all these aspects, I could go to the black holes, and then I will see how it is possible to describe quantum black holes in loop quantum gravity, to describe the microstates, to count them, and to get the famous Bekenstein-Hawking formula for the entropy. And I will also conclude with the case of the Rotantic black hole, because what we know how to do so far is, we know very well how to treat the Schwarzschild black hole, so spherical black hole and no rotations. But now it is possible to go to the rotating case. Okay, so the first part concerns loop quantum gravity in a nutshell. So in the motivation, in the introduction, I said that HTK variables is based on this action of gravity. So what is this action? More precisely now, this is a first order formulation of gravity where the fundamental variables are spin connection, omega, and a triad, which is related to the metric in the usual way. And here we have a trace in some Lie algebra, and the Lie algebra behind this formulation is the SL2C, so the Lorentz Lie algebra. Here is the Hodge dual. So to describe precisely, it's not very necessary to describe precisely this action, but I just would like to say that, as I said previously, when you write the equations of motion with respect to omega, you can find that omega is in fact the Levi-Civita connection, and if you plug back the solution for omega in the action, you recover exactly Einstein-Hilbert action for gravity. So in that sense, this is completely equivalent to the usual Einstein-Hilbert action. And then, if you perform, the gauge group is the Lorentz gauge group.
When you solve the equation, oh, sorry, that's the Lorentz gauge group that you're using for your connection.
Yeah, exactly. Yeah.
Not the SU2.
No, this is SL2C. Yeah, the whole Lorentz group. Yeah. And then, but the thing is that, as I'm going to say later, it is possible to partially gauge fix the theory before going to the quantization. In fact, this is what we do. If you perform the Hamiltonian analysis of this theory, you obtain a pair of canonical conjugate variables, exactly what I said previously, a connection, A, and the electric field, E. And in fact, when gamma is a complex, originally, when Ashtekar discovered this variable, he started with gamma here, which takes the value I, the complex number I squared is -1. So in the case where gamma is I, indeed, this theory is SL2C invariant. In fact, it is also SL2C invariant for any value of gamma. But to do the Hamiltonian analysis is much easier to partially gauge fix the theory and to break the symmetry group into SU2. And indeed, this Poisson bracket here is based on an SU2 gauge fixing of the theory, which is called the time gauge in the case of first order gravity. So we have this Poisson bracket here between A and E, and the theory is a gauge theory, so the Poisson bracket, they don't come alone, they come together with a set of constraints that are closely related to the symmetries of the action, as usual. And the different constraints that we have are a Gauss constraint, which generate SL2C gauge symmetries or SU2 gauge symmetries when you partially gauge fix the theory. You also recover the standard vectorial and scalar constraints, which generate space-time diffeomorphisms, as usual. And so this is the formulation of the standard Ashtekar or first-order formulation of gravity. And now there is one more hypothesis to understand before going to the quantization. And this hypothesis is sometimes called the polymer-states hypothesis. Because we know that when we have a phase space, then the quantization in principle follows immediately. Because we turn, this is the x variable, if you want, the position, we have the momentum. This guy becomes an operator, which is the multiplication, and this guy is the derivative, and then we look for the quantum states, which are solution of all these constraints equal 0 once we quantize these constraints here. But this is very difficult to do, and the idea to find a nice quantization and to find a nice quantization in the sense that to find a way to solve some quantum equations coming from the Hamiltonian analysis, we make this hypothesis. So far, what we found is that the phase space is the cotangent bundle of SU2 connection. In other words, phase space consists in connections SU2 plus the conjugate momentum, which is called the electric field. And this space is very complicated to quantize because it's infinite dimensional, it's very, and of course, having a connection at each point of the space is something very, very complicated. And to have a quantization, having a quantization of this space is related to having a definition for the path integral of gravity somehow. So this is something that we cannot really do, quantizing the full space, the full phase space as it is written here. So the idea of low quantum gravity is to say that in fact the fundamental excitations are somehow one-dimensional excitations. You know, instead of working with the full SU2 connections at each point of the space, we work instead with what we call the holonomy of the connection. So now we have lines drawn on the space, which is a topological space, and then the connection has a non-vanishing value only on one-dimensional excitations. Okay? And then we can define this connection A of E, which is the path integral of A along this line. Conjugate to these excitations, to this fundamental excitation, we define electric field. So now, these electric fields are very easy to understand. Once we have a line in 3 dimensions, you can define this, a surface which is tangent somehow to the line. And you have a surface, a natural surface here, and you integrate, you smear the electric field, which is the 2 form, on this surface here. So now, the variables are the following. You have a kind of graph in the space. On the lines lives A, the X excitations, and on the conjugate surfaces, you have the momenta, which are this electric field which are smeared on the surface here. And now, fundamental excitations, as you see, are one-dimensional. And the idea is to say that, in fact, the states, the quantum states we're going to compute, are functions of these guys. And the functions of these holonomies are called cylindrical functions in this context for different reasons. Yeah, all possible graphs on the space. Okay, and this can be done using. I will come back to this because for all this for the moment is classical, so it's possible to define it. And I agree that when we take all possible graphs, we need to show if the Hilbert space is well defined. And there is a uniqueness theorem which says that this full complicated Hilbert space is endowed with a unique Hilbert structure. This is one of the main aspects of low gravity. But in this formulation, what is nice is also that the symmetries that we have to take into account to solve, to quantize the theory have a very simple formulation and very simple interpretation. The Gauss constraints, which generate SU2 transformations here, are just given by, if you have a connection A, then you conjugate. This is just the adjoint action of SU2 on the connection. So standard action, the same action as we have in gauge series. And space diffeomorphisms, for instance. So now we have a connection on the line. We perform a diffeomorphism. This makes the line moving a little bit. And then when the edge E moves to phi of A, this function A of E is transformed to this. So the space diffeomorphisms have a very simple interpretation in terms of these variables here. What remains to understand is the Hamiltonian constraints, what we still don't know how to quantize, in fact. So this is an open question. There are many different techniques to try to solve this problem of the Hamiltonian constant, but I will not discuss this in this paper, in this talk. And also, we have similar actions of these symmetries on the momenta here, the electric field variables. So for the moment, everything is classical, but as you see, if we assume that, okay, fundamental excitations are one-dimensional, then we have a well-defined phase space with where symmetries act as automorphisms on this phase space, and the action are very, very simple. And now we can start thinking about the quantization. This A and E? Yeah, as I said here, E is a vector field. So if you want, A and E are conjugate. Okay? When you have A associated to a link and E associated to a surface, if they cross, if they meet at a point, there is a non-trivial Poisson bracket, and the action of E on A is just a vector SU2 action, left or right SU2 action. Because you see, this guy live in the Lie algebra of SU2, and there is an action of the Lie algebra SU2 on the group SU2. And this is a standard left or right action. It depends on um, on the prescription that you choose. But that's a very simple action, in fact. And now, as I said, we can think about the quantization. So I will not give all the details, just the main results that will be useful for understanding black holes. So what we know, what we have at hand is a quantization of what we call the kinematical space. Kinematical space because we consider only the Gauss constraint and the space diffeomorphism constraint. And as I said, the solution of the quantum space I'm going to present you is not concerned by the Hamiltonian constraint, which contains the information on the dynamics. So in that sense, we call it the kinematical Hilbert space. And one important theorem is that if we look, so we have this phase space, we quantize it as usual. X and P are non-commutative they become non-commutative operators. And we look for representations of this quantum algebra, as usual. In the case of quantum mechanics, a point particle on the real line, we know that X and P have a unique representation due to Stone-Weinemann theorem, which says that X is the multiplication and P is the derivation acting on the space of functions on the real line. And here we have kind of similar unicity theorem, even if it is quite different to what we have in quantum mechanics, but at least we have this unicity theorem. It says that if we start with the phase space and then we quantize it, we obtain an algebra, a quantum algebra of non-commutative operators, a non-abelian algebra, then we look for representations. The point is that if we want these symmetries to act naturally on the representation, by naturally, we mean that the standard properties that we need in quantum theory, we want a unitary action, we want them to be automorphism, and then if we ask that, for instance, one important property is that this representation is invariant under diffeomorphisms, then there is a unique representation that can support this diffeomorphism invariance. So here, it is possible to construct the kinematical hyperspace, and not only it is possible, but also we have a unique prescription to do that. And this can be done using what is called Gelfand, Naimark, and Segal construction for any quantum algebra. So this is a strong statement that says that if you impose diff invariance, which is something that comes from, of course, general relativity, then you end up with a unique kinematical Hilbert space.
The Hamiltonian constraint usually has to be imposed also at fixed t, at fixed time.
Yeah.
So are you sure it's irrelevant for this kinematical discussion?
No, I'm sure that is not. What I'm sure is that it is really important to have a solution of the Hamiltonian constraint. That's for sure. The only thing what I'm saying is that if we impose only the first two families of constraints, then we get this. Probably, if we impose then the last constraint, we may have something different. For the moment, we don't know. We don't really know how to do. I mean, there are different proposals, but they are not complete and not totally consistent, I would say. But I agree that we need to impose the Hamiltonian constraint to have the full thing. Yes, for instance, it can reduce it, or maybe not. It can be completely different as well. And this is a question. This is an open question. I totally agree. But if it does reduce this phase space, that's fine, because if the physical Hilbert space is just a subspace of this of the Hilbert space we obtain here, that's okay. This means that we are in a good way to the full quantization of gravity. But so we have this construction, and let me now explain you in words quickly how these states look like. In fact, there is a basis of this Hilbert space, so there is a unique quantization. This means that now we have a Hilbert space of states of quantum geometry. We call them states of quantum geometry because these are interpreted as three-dimensional quantum states. And there is a basis of this Hilbert space, which is given by the spin network basis, and spin networks are just generalization of Wilson loops. So how does this work? As I said previously, at the classical level, you remember that we don't work with the connection at each point anymore, but we have these one-dimensional excitations. And this means that a state, a quantum state, will be labeled by a graph with one-dimensional excitations, and this graph contains lines like this and also nodes. What we can, and all these lines, they carry, in fact, the path integral of the connection, the holonomy of the connection, the SU2 connection of HTK. So when you have a graph, the graph allows you to define a quantum state, exactly as when you have the number n, l, and m for the hydrogen atom, you get the wave function, one wave function for the hydrogen atom, exactly in the same way. So this graph, they label quantum states of the geometry. What we can show that, okay, so we have this one-dimensional graph which contains the quantum excitation of gravity. What we can show that if we impose the invariance under SU2, the graph must be closed. And also, so this means closed, there is no a line which is open. So all the lines, they meet at a point like this graph here. And each edge is in fact labeled by a spin, by half integers, 1/2, 1, 2, 3/2, and so on. And these integers, they are the representation, unitary irreducible representation of SU2. So these graphs, this basis is in fact constructed using the harmonic analysis on the SU2 gauge group. And so now each link of the base comes with a half integers, with a half integer, and at the nodes, we have what we call intertwiners. Intertwiners are just Clebsch-Gordan coefficients, and these Clebsch-Gordan coefficients are needed to make the whole state gauge invariant. So now a quantum state is just a graph. Each link is colored by a spin, and each node is colored or is associated to a Clebsch-Gordan coefficients, an intertwiner between SU2 representations. And the interpretation of such a graph at the kinematical level, again, is very simple. Because now we have a graph and we can compute the action of some operators on the states exactly as we compute the action of the Hamiltonian on the states of the hydrogen atom, exactly in the same way. So in geometry, the natural operators are the area operator associated to a surface like this one. So it is possible to quantize the area operator in a very simple way. And when the area operator associated to this brown surface here, for instance, act on a spin network like this one, so here you need to complete the graph. I just have drawn the part of the spin network which is above the surface here. Then you can show that the area, these states here, in fact, they diagonalize the area operator, and the spectrum is discrete. And this is exactly why we say that space is discrete at the Planck scale for loop quantum gravity, because when you act with the operator on the states, then you get a discrete spectrum, and L here are the spins associated to these edges. Which scale? This, yeah, it comes from the commutation relation, which comes from this Poisson bracket. That's it. Yeah. Okay.
The two operators are emission, so the commutator should be anti.
Yeah, I agree. All this is true only when gamma is real. Yeah, that's important. All what I did here is true for gamma real. Then the point will be, how do we get back to gamma equal I? This is what I'm going to discuss now. Yeah. So what we have here, yeah, is this spectrum with gamma real. And what we can show is that the volume operator is also an operator that acts on the spin network like this, and we can show that it acts on the nodes of the spin network. And again, we find a discrete spectrum, but the spectrum of the volume operator is more complicated. These guys, they don't diagonalize the volume operator, so the action is more complicated. This is the reason why I haven't written it in here. And so we come to this picture of the space at the Planck scale, where from the kinematics, again, so we don't have dynamics here, the space is discrete. And to this is exactly the same graph as Carlo shown in this talk, but to each to a graph like this one, we associate a kind of picture of the space like this one. Of course, this is just a picture, but just to say that to each node we have a volume. So to this node here, for instance, you associate the volume of a domain on the space. Here, this is a sphere, and each edge comes with a quantum of area, and this quantum of area, in fact, gives you the area of the intersection of the ball here and the ball here. So you see, so this guy here is just the surface of the intersection of the disk somehow between this ball and this ball. And this is the picture that we can get from loop quantum gravity. Okay, and as I've just said again, edges, they carry quanta of area, while the nodes carry quanta of volume, and that's it. So this is the picture that we have for the space in loop quantum gravity. Many questions remains to be solved, as the problem of the dynamics again. But at this level, at least, we can start thinking about the physical consequences of this picture on black holes, for instance, and on cosmology. And I will focus on the case of black hole, and I will show that it is indeed possible to have, using this picture, a very nice description of quantum black holes in loop quantum gravity. So how this picture allows us to understand the black holes. The first thing, so this is a classical picture of the black hole. All what I've described so far is the quantum state of a space with no boundaries. So we have a space which lives on the three-dimensional space manifold, let's say, and these states label quantum geometry. So now, how can we describe the presence of a black hole in this picture? So if I consider here the classical description of a Schwarzschild black hole in the Penrose diagram, in fact, we consider the horizon of the black hole as a boundary in the case of loop quantum gravity to describe the black hole. So this is a 2D picture, of course, but this point here, any point, this is the horizon of the Schwarzschild black hole, and this point is a two-sphere, like this. So we have this boundary, and for this boundary to be a horizon for the Schwarzschild black hole, we need, of course, some geometric conditions on the boundary, and these geometric conditions are the standard one for the horizon: null surface, no expansions, and other quantities that comes from the HTK formulation of gravity. And again, all what I'm going to talk about for the moment is restricted to the case of Schwarzschild black holes or spherical black holes. There is no angular momentum for the moment. The point is that if we want to have a quantum description of black hole, we need a Hamiltonian description of the black hole, because loop quantum gravity is based on a Hamiltonian quantization of pure gravity. So now, again, we would like to have a Hamiltonian formulation of gravity in the presence of a boundary, this boundary, where we have some geometrical condition. So without going into the details, what we showed, so there is the reference is hidden here, but what we can show is that for the Hamiltonian formulation to be well defined on this space here, so here you see we have two Cauchy surfaces, M1 and M2 at two different times, and if we want again the Hamiltonian formulation to be well defined, we show that at the boundary we have a new variable which is an SU2 connection, and this SU2 connection comes with a Poisson bracket, a symplectic structure, which is the Poisson bracket of the Chern-Simons theory. So at this stage, what we say that, okay, if we have a black hole, then necessarily the black hole is described by a Chern-Simons theory with the gauge group which is SU2. And we know very well how to quantize and how to describe SU2 Chern-Simons theory, and then we will use all what we know on Chern-Simons theory to describe the quantum black holes. And the picture is the following. So now you see the boundary is a sphere. And at the quantum level, what do we have? We have all these excitations, because we know that quantum geometry states are labeled by these graphs, which lives on the space manifold M1 and M2. These graphs here, they come with edges, and these edges, they cross the boundary. And we need to say what happens to these edges that crosses the boundary. And the way we're going to describe the crossing between these edges and the boundary will allow us to define, in fact, the quantum states of the black holes. This is what is going to happen. So again, we have a strong relation between Chern-Simons theory and black holes. Why? Because, as I said, these black holes in low quantum gravity are described in terms of an SU2 Chern-Simons theory, and the Chern-Simons theory is given by this action here. This is the 3D actions, which lives on the horizon. And the Chern-Simons theory is defined by a gauge group. So this is fixed by SU2 because we have this SU2 connection in the bulk. Chern-Simons theory is also defined with a level, K. So this is a coupling constant. And the coupling constant is related to the area of the black hole, like this. And you see gamma still appears here. And you see immediately that the semi-classical limit happens when the level becomes large. This is what we expect from a semi-classical Chern-Simons theory. And also to define the Chern-Simons theory, we need the canonical surface we work on. And this canonical surface is a two-sphere, because this is just the horizon of the Schwarzschild black hole. And this horizon, as it is shown in this picture, is punctured by links. And these links, they are colored by spins. So here we have a sphere which is punctured, and these punctured, in fact, they describe singularities or conical singularities in the case of Chern-Simons theory. So what we are going to say is that, okay, so now we have a well-defined Chern-Simons theory, we have the surface, we have the gauge group, we have the level, let's go to the quantization. And this is... Sorry?
K is integer.
Yeah, it must be. When you quantize, K must be an integer. Yeah. Yeah,
I know that in the spin network we cut a hole in, and it's actually a black hole we cut out, as opposed to just some random sphere and that piece of space.
Yeah, I agree. The thing is that the important input here are these geometrical conditions that allows you to describe the horizon in terms of a Chern-Simons theory. Having a Chern-Simons theory, it is something non-trivial, and this Chern-Simons theory is here because we have a black hole and not just a chunk of space which is anything. This is really important. Chern-Simons is really related to the fact that we have a horizon.
I think one indication the black hole is the Chern-Simons theory, but it should also be a feature of this model that you cut any sphere out of the universe.
Yeah?
Wherever it is, the entanglement entry across the diamond goes like the area.
Maybe, but
So if you have this algorithm, you get a convenient way of describing that. But what I can't see is how this complex grid of stuff is going to show me where a black hole is or is not.
But the thing is that what I'm going to compute is not the entanglement entropy of the black hole. I'm going to not only to compute the entropy, but also to describe the microstates of the black hole. So we have many informations, not only the entropy, microstates, and we count them in.
I guess the question I asked is really, how do you know if you've got a black hole as opposed to some piece of space? And how if we calculate microstates of something, is it a space, a piece of space, or is it something I'd recognize as a black hole?
How do you recognize it's a black hole?
Yeah.
At the quantum level, you mean, or?
There should be some correspondence.
Yeah, I agree. Again, the fact that we have a black hole is contains on all this. Here we have all informations that say that this is indeed a black hole.
Karim, should we impose some condition on A?
Yes, of course, we have to impose.
Which specifies with the
Yeah, okay. The condition on A, these conditions are typically the fact that the metric is due of a Schwarzschild metric. That's the point. So
What
he.
is the symbol F proportional to
Oh yeah, sorry. Yeah, this is just a technical. F is the curvature of the connection, the curvature of the Chern-Simons connection. In fact, this equation here,
E is the electric field?
and E is the electric field, exactly. Yeah. So we have set condition here to describe the black hole. So yeah, I didn't want to go to the details, but I can show you how, in fact, this condition here relate the connection in the bulk, and E is the action of the electric field on the boundary. And yeah, of course. Yeah, it's not Maxwell, it's gravitational electric field. Yeah.
They try it. And that's the electric field of your gauge field.
Yeah, exactly. The electric field. Yeah. Yeah.
So that's an SU2 gauge theory, which is sort of on a time on a surface which has time included, right? Is that what you mean? In 3 dimensions.
Yeah.
To get the electric field from a two-form,
Yes.
normally they take the inner product of the time-like vector.
No, this equation is just an equation between two forms. F is just the curvature, which is a two form on the on here, and E is also the two form. Okay, E is just the E is not the triad, is E wedge E. So maybe this is the reason why I haven't written the relation, the explicit relation between capital E and the small e, which is a triad. But this is a relation between two forms. Yeah.
The inverse is Italic type.
Okay, so we have this, and we believe this is a black hole. So maybe this is something we can discuss. But the nice thing is that now we can quantize the Chern-Simons theory completely, and this is very well known. We can quantize it in the case of SU2. So again, we are still in the frame where gamma is real, and then the gauge group is a compact gauge group. And so we can, there are many ways, in fact, to quantize Chern-Simons series. The first original one is due to Witten a long time ago, and then it is possible to compute explicitly the path integral of Chern-Simons theory using some regularization techniques. And this path integral leads to the fact that indeed K must be an integer for the theory to be well defined. So this is what you ask Noui. So in that case, the level must be an integer. And when K is an integer, then it is possible to regularize this path integral. And what you obtain at the end of the day is in fact that the path integral of the manifold M, and then also we can have observables inside the Chern-Simons theory, which are labeled by knots. We get knot invariance and manifold invariance from this quantization. And this is the way that we can relate gauge theories to knot invariant theories, and this is very well-known work. There is another way which is more interesting for us to quantize the theory, and it is a Hamiltonian quantization. Sometimes it's called a combinatorial quantization, and low quantum gravity is a Hamiltonian quantization, so this is a nice way to understand how quantum states for the black hole will emerge. In fact, so without going to the details as well, but it's possible to have something very precise. You see that we have this space with links that cross the horizons, and all these edges that are colored with SU2 representations. And in fact, what the quantization of Chern-Simons says, it says that the Hilbert space for the quantum states of the Chern-Simons theory are given by intertwiners between all these representations crossing the horizon. In other words, you will have a microstate for the black hole. All the time, you can construct a singlet in the tensor product of all the representations crossing the horizon. To be more precise, we have a quantum group instead of a classical one, but to understand the semi-classical properties, we can just turn this quantum group into a classical one. The quantization is not relevant for the semi-classical analysis. So again, now you have this sphere, and you have these representations crossing the horizon. And in fact, what this quantization says, it says that to have a well-defined quantum states, all these guys, they have to meet somehow inside the black hole at a node, and this node contains an intertwiner. So we have to construct a singlet in the tensor product of all these representations. And this is the well-known physical Hilbert space of the of Chern-Simons theory, and also we can compute the dimension of this guy. So there is formula due to Verlinde here using conformal field theory techniques, and we can also compute this using the quantum group techniques, but you obtain a closed formula for the dimension of the Hilbert space. So the question now, which is naturalized. Okay, so we have this quantum state. So we are saying that, in fact, quantum black holes are described in terms of intertwiners. We know how many of them there are. Let's compute the number of these microstates and see if at the semi-classical limit we recover the Bekenstein-Hawking law. And this is something that we can do. And as you may know, indeed, now we use the previous formula, this one here, the Berlinde formula, and then we consider the limit where the area of the horizon is much bigger than the Planck scale. And this corresponds to k goes to infinity, okay, the semi-classical analysis of Chern-Simons theory. And as I said previously, in that case, black holes, microstates, are classical and not quantum intertwiners, so they are singlet in some tensor product representation. The previous formula reduces to a very simple integral here. The d are just related to the j variables by this formula. D is the dimension of the spin j representation in SU2, so just an integer. And then you have this, and you can compute the asymptotic properties of this formula in this limit. And this has been done the first time in 96 by Carlo here, where in the case where all the spins crossing the horizon are the same and they are spin 1/2 for simplicity. And provided that you fix gamma, this free parameter, to some value, that I didn't show up here, you get the Hawking law plus some quantum corrections. Okay, so this was the first indication that maybe what we are constructed are indeed quantum microstate for the black hole. And this works, again, when you fix gamma to some special value. This calculation can be generalized to the case of any spin, not only 1/2, and then we have a more complicated formula, but we get back to the same semi-classical area law at the end of the day. So the question here is that gamma plays a very intriguing role, and it is completely natural that it shows up here in the computation of the black hole, because gamma enters in the Ira gap. So it is completely natural that you get a gamma in the black hole entropy as well. So why fixing gamma to recover the black hole entropy? We can think that maybe if we consider cosmology, for instance, if we have a way to measure the maximal density of the universe and you compare it to the calculation of loop quantum gravity, we may have another different value of gamma if you consider Kerr black holes as well, and so on and so on. So it's not completely obvious that we get exactly the same value of gamma for different experiments. So it will be nicer to get something which is independent of the free parameter, and also because gamma has no classical interpretation at all and no classical relevance. So there are different scenarios to address this issue, and I will go to show you how we can get rid of this gamma, going back to the initial HTK variables and setting gamma to this complex number. There are many reasons to do that. The first reason is that HTK, the Hamiltonian constraint is simpler in the case of in that case here, and the other reason, which is maybe deeper, is that the fundamental HTK connection, it is a 4-dimensional space-time full connection when gamma is complex. But when gamma is real, this HTK-Barbero connection is not a full space-time connection. It is just a space connection. And the fact that it's not a full space-time connection, this means that, in fact, the physics we are studying depends on the slicing we are considering for the Hamilton analysis. And going to this value is deeper because we are working with an object with the connection, which it is a full space-time connection. Then we expect that the quantization to be completely independent on the choice of the slicing. So somehow we have a covariant quantization, a covariant Hamiltonian quantization. So how do? We go to the notion of complex black holes. This is the thing that we developed the last years with my collaborators. And the idea is that we know that it's not possible to start with gamma complex and to do the quantization. Because if you start with gamma complex, we have this SL2C gauge group, and then we don't know how to handle this non-compact complex gauge group. We don't know how to start the quantization. So the idea is to do exactly what we do usually in gauge theories or in quantum field theories. We do kind of Wick rotation. We start with the SU2 formulation. We have this gamma. We play the game. We do all the quantization. And at some point, we have to go back, doing by an analytic continuation to the case where gamma is plus or minus I. So this is what we did. So gamma plus to when gamma takes this value, the level now becomes complex. This is what we expect from a Chern-Simons theory. When you have SL2C instead of SU2, then we expect the level to be complex. This is what we have. And as I said, this Chern-Simons theory is much more complicated to quantize, and we don't know how to quantize directly. The only way to perform the quantization relies on some analytic continuation techniques. Okay, so this was initiated a few times ago by Witten, for instance. And now we have this entropy computed in the case where gamma is real, and this entropy is the dimension of the Hilbert space. So therefore, it is an observable of the Chern-Simons theory. It is a function which has a physical relevance in the case of Chern-Simons theory. We have this observable, so we can just complex continued the formula that we have in terms of when gamma becomes complex. But there is something interesting happening, is that you remember that all the time you have an edge crossing the horizon, then this edge comes with a quantum of area given by this formula. When gamma is complex, then you have an area complex. But to have an area which is still real when gamma becomes complex, then the j here, the integer, must become complex. And this is nice because this shows that when gamma becomes complex, you send SU2 representations into the non-compact SU11 representations. So here, you recover the Lorentz structure of the horizon. So doing this analytic continuation is interesting because as we will see, it allows us to recover the Bekenstein-Hawking law, but also because somehow it says that the real physics is Lorentzian, and then instead of having a space horizon, then somehow we recover SU11 with the Lorentz signature. So if we do that, so that's possible, it's just a technical point. We have this formula for the number of microstates. So this is the exact formula when gamma is real. So it can be written in terms of an integral on the complex plane with a contour here. And then if we do the analytic continuation, which means that gamma becomes complex and the representations here becomes complex as well. So we have SU11 representations. There is a unique non-trivial choice of the contour to make this analytic continuation. And then what we get is, after some calculation, exactly the area law, at least for the leading order term. And this works only when gamma is equal to plus or minus I. So this is really interesting because if you had taken some other complex value for gamma, you would not have recovered this A/4 without fixing gamma to very special value. So the value gamma equals plus or minus I plays a very interesting role. And so maybe, yeah. And also, what we can show that in this kind of, in this description for the black hole, now the quanta of area are described by a real number, which is S here. And then at the semi-classical limit, we have the color of the graph of the link, which become very large, the number of them which becomes very large, and then we get, after some calculation, to this formula with exactly A/4. So, yeah, this is just the correction, the small correction, and this is something we don't control for the moment. Small O, small. Okay. So that's okay. It has to be I. No, I. Yeah, times 1. Yeah, exactly.
And do you get this log corrections?
No. Yes and no. No, because the simpler model, they don't lead to these log corrections. But if we complexify the model, then we can get back these log corrections. But so far, we don't. I would say that we don't really understand how to get the log corrections. We only have this, but all this is just, I mean, we have to understand better what this analytic continuation means, I think, to go to this log correction. There are many things to understand before. But what is very interesting is that, yeah, we obtain exactly A/4 for the HTK variables. And then we have to see whether this construction was robust or not, we tried to generalize to different situations. Well, okay, so this is just a technical point, but for the BTZ black hole in 3 dimensions, it is also possible to play the same rules, same game, and then we obtain exactly the good formula for the BTZ black hole. In 3D, we know how to quantize exactly the theory. It is also possible to have an understanding of the Hawking radiation that I haven't talked about here. And again, as I said in the introduction, it is also possible to generalize this construction to the case of rotating black holes, what we didn't have before. In the case of real SU2, when you consider the SU2 description for the black hole, then there were a problem because introducing an angular momentum would not lead to the Bekenstein-Hawking area law. But here, using this analytic continuation techniques, we still get the Bekenstein-Hawking law, which is totally consistent with the semi-classical analysis. So now I conclude. And so we have strong results which support the idea that maybe in low quantum gravity, when we send gamma to plus or minus I, we have a nice description of the quantum, the microstate for the quantum black holes. This has been shown in the context of black holes here, but what I haven't shown is that we have also tested this idea to the case of 3D gravity, where everything is exactly solvable, so we can quantize the theory exactly. And then we check that if we apply the techniques of low quantum gravity to 3D gravity, then we see that indeed, in that case as well, we need to send gamma to plus or minus I to obtain the right quantization of 3D gravity. So this is a nice testing ground for this idea, and it seems to work. And maybe we have to go further to see whether the scenario is robust, is even more robust. Looking at the Hawking radiation, as I said, there are some scenarios which have been proposed, but so far there are many things that are not understood yet, and also people like Carlo Rovelli are studying. They started studying this information loss paradox, and they came to these Planck stars you have just discussed, and all the consequences related to this description. Okay. Thank you.